All right, so over the next couple of days, I'd like to get through this handout, kind of deciphering. You upgraded. Decipher whether we should use the T distribution or the Z distribution. Okay. My hope is that we get pretty proficient at this, because eventually we're going to have to do something called a T test, and we're going to have to decide what distribution to use for that. Okay. So this first question says a college admissions director wishes to estimate the mean age. Okay, so that right away tells me something from my diagram, from that chart we made a couple days ago. Okay, we're looking at means here. So if we go over to our chart, means. So basically it tells me we're going to go down this branch. Okay, this stuff on the right, we haven't even talked about proportions yet, so obviously that would be another reason why we wouldn't go down here. But we're going to go down, talk about means. So now I'm going to get to here and say, does N, is it greater or equal to 30 or not? So as we go through, it says in a random sample of 20 students. So that's less than 30, so we're going no. Okay? Now, here's the thing. Ultimately, regardless of whether we answer that question yes or no, it's going to get us to the statement of whether our proportion our distribution is normally distributed. Okay? If N was greater than or equal to 30, that guarantees it. Does that make sense? Okay. If N is less than 30 and we know nothing about our population distribution, it could be normal or abnormal. We don't know. Okay. But if N is less than 30 and they continue to tell us more information, they say the population is normally distributed, that'll be a good thing for us. Okay. If we don't know that, that'll be a bad thing for us, because we haven't talked about these things over here in red. Okay, so as we continue to read the question, random sample 20 students, the reason if it's bigger than 30 is that the central limit theorem kicks in. Okay, and then we could just say that, okay, well, if it's bigger than 30, then the sample means they're going to be normally distributed as well. If it's less than 30, that doesn't kick in unless the distribution they're coming from was normally distributed itself, or the population is normally distributed. Okay, so it goes through this, says the mean age is 22.9. Says from past studies, the population standard deviation is known. That might be something I want to highlight here, to be 1.5 years. And the population is normally distributed. So that's key. It is normally distributed, so we can go down here to yes. And ultimately what we're trying to do, no matter whether I went down the branch that it was greater than 30 or less than 30, is this question right there. Is the population standard deviation sigma known? It was. We highlighted that, right? So then we're going to use what test? Or what distribution? Z distribution. Okay? So we got to use our Z distribution. So I'm going to write down here what the margin of error is for using a Z distribution. It's Z of sigma over 2, or sorry, alpha over 2, and then sigma divided by square root n. Okay, and then our interval will be x bar, our point estimate, minus the error, less than mu, less than our point estimate, plus the error. So now what we want to do is figure out, well, what is the point estimate? $22.9. Okay, and what we're talking about there is that is the mean of those 20 students. Okay, if I were to take another 20 students from this population and calculate their mean, it's probably going to be different than 22.9. Does that make sense? If I do it again, it's probably going to be different than 22.9 or that second number that I found, the second sample I found. So this number is going to vary per samples. Okay. A point estimate, you kind of look up here on this whiteboard, okay? If I have a confidence level of 0%, then that means I'm using a point estimate as my interval, okay? I put quotation, it's really not an interval if I'm using a point estimate, right? It's a singular value, okay? But the idea is, why am I 0% confident in my point estimate being the exact same thing as my population mean? My sample mean is never going to be identical to my population mean. Does that make sense? Okay. If I have, think about this. If you have, let's say, 1,000 people, and you want to find the average of their weights, chances are that you're not going to take out 10 people and find that 10 people's average and it beat exactly the same as the 1,000 people's average. Does that make sense? It's not going to happen. Okay. But if I want to increase my confidence level, then all I do is I widen the view of that point estimate. So I'm going to widen my interval a little bit and include more values, and I'm going to have a higher level of confidence. Well, if I want to increase my confidence all the way up to 90, 99%, that means my interval has to widen. Does that make sense? So the larger your confidence level, the greater or wider your interval is going to be. But 22.9, and I'm going to show you a simulation here in a minute that kind of shows and demonstrates that idea maybe a little bit better visually. So that's my point estimate. We know the population standard deviation, okay, 1.5. Now, generally, we don't know that because, remember, we are trying to find an estimate for mu, right? Well, if you think about how you find the population standard deviation, it is this formula. Capital N. That's the formula for finding the population standard deviation. What is in that? Mu, my population mean, right? Well, it doesn't make a whole lot of sense that if I know this but don't know one of the items or tools that got me that. Does that kind of make sense? Okay. So generally speaking, the only way that we're going to know the population standard deviation is if we are a follow-up study. Okay, somebody's already done a study and we're trying to confirm their results, and we're going to do a study again, and that we can use their previous data to give us a good idea of what the population standard deviation is. Does that make sense? And like if we were doing a study, first study of its kind, no data, we would not know that. Okay. So we got that. Now we can go ahead and figure out, N obviously was the 20. Now we got to find out Z sub alpha over 2, right? Okay. So my confidence level, they want us to be 99%. Okay. That means alpha is 1%. I haven't said this, but sometimes they will refer to as alpha as what we call the level of significance. Okay, it's just the complement of your confidence level of significance. But alpha over 2 then, because a normally distributed variable is symmetric, alpha over 2 is going to be 0.005, right? Now, we're going to think about what are we doing, what do these values mean for us for finding our Z value. Okay, we want the central 99% of our data. So let's say this thing here is mu. Okay, we're trying to estimate mu. We want a confidence interval that is going to incorporate or encompass 99% of our area right there. Okay, that means that area there and that area there total to give you your level of significance. They total will give you that 1%. Because it's symmetric, that's 0.005, and that is 0.005. Okay. Now, using your table, I'm going to show you how to do this table. We have to figure out what the Z is. Okay. If you remember, or you have the notes from previous sections, I said that if we go 90%, you can attach like a 1.64. I think I even wrote 1.644. If I was at 95%, that was the 1.96, right? and 99 was 2.58. Okay. Now these are approximates. Okay, approximations. Okay. And out to 2 decimal places is perfectly fine for us. But I want to look at this table 0.005 because on a test or quiz it might, especially if I'm using Math Excel, they will take like this value here and let that be a variable in the way the question's written. And in the background, they'll say, okay, so they'll call this like, we'll call it like var1. And in the background, var1 will be allowed to take on values between 90 and 99. And it will randomly choose a number between those. Does that make sense? So you might get 93, or you might get 95, or you might get 97. But you got 95, you're okay by memorizing these values here that I told you. But if you got 93, you don't know any of those, right? Okay, so I want you to be able to use the table. I want you to be able to use some type of technology to help you realize this. So here's a Z table. Okay. We're looking for, so we got the area 0.0. So this one right here, this area would be 0.005. Okay, and that's how all Z tables are going to be constructed for the most part, are going to be cumulative to the left. So I think it makes sense to find that left-tailed area. So I'm going to find 0.005 in here, and it's kind of like right there, correct? Okay, we got 0.0051 and 0.0049. So I come over here, it's negative 2.5, and this is 0.07, this is 0.08. So right now we're seeing, obviously 0.005 would be smack dab in the middle there, right? Okay, so through a process called interpolation, we can say, well, it falls between negative 2.57 and negative 2.58. Okay, so 0.005 should fall between those two numbers. Well, if 0.005 is exactly between those two, then we should be looking at negative 2.575, shouldn't we? Out to a third decimal place of precision. What I want to do is I want to use technology. So what that number I've given you to kind of memorize and use on your own rounds to the hundredths place, right? Sees that 5 and rounds that to an 8, right? Okay, which is fine. But what I want you to see is that even though this table is used in many aspects, okay, heavily used throughout all statistics, that number probably isn't 0.0051. Okay, that one's probably not 0.0049. They're rounded. Does that make sense? Okay, so I want to take and look at, for our purposes, negative 2.58 is fine. Negative 2.575 is fine. Even if you use this, you would be good enough. Okay. But if we use our calculator, okay, so you go second distribution, which is the var's key. I'm going to go down to 3, which is inverse norm. And it takes me here. Okay, and I'll show you. So some of you, it will take you here. Some of you, it won't. I'm going to type in the area that I'm interested in. So this is the cumulative area from the left. So I want 0.005. It's a normal distribution, so I'm just going to leave sigma at 1 and mu at 0. And if I hit paste, we're good to go. Okay. Now, if you don't have that structure where it takes you to that page, asks you to fill things in, that's fine. Or if you forget where that's at. If you forget so the pathways to get to a lot of your functions on your calculator can be confusing. Does anybody know how to find all of them at once? If you hit second and then your 0, see how it takes you to the catalog? Every function throughout your calculator is then listed in alphabetical order. Okay? So if I wanted to find inverse norm, I just got to scroll to the i's. Now, what is nice is that you should be able to click on alpha and then I. Alpha. There you go. And it'll take you to the i's, and then just scroll down to find inverse norm. Okay, if you forget where it's located. Now you see the way I did that, it didn't take me to that page, did it? Where it asked me for my area. So if you have an older calculator that even if you go to second vars and takes you to distribution functions and you hit inverse norm, it might take you straight to this. So you type in 0.005, it's your cumulative area, and then you have to hit comma, which is right above the 7, okay? And then it goes mean, and then standard deviation. Okay, the way I remember that is just alphabetical. Mean comes first, right? Hit enter, and we get that number right there. Okay? Do you see how that number is not exactly this number here? Does that make sense? And the reason for that is because this number of 0.0051, if I use normal CDF, that's fine. Upper, I want to go to negative 2.57. That 0.0051 number, in all actuality, is 0.00508495541. Does that kind of make sense? Okay. So these are all rounded. However, they're rounded to a precision that is going to be good enough for pretty much all statistics that we do. Is that okay with everybody? Why am I saying this? Because some people will use this number directly as their z sub alpha over 2, which is fine. Well, if I use that in my calculation, but you used 2.58, our answers are wrong or different, right? And it's just the difference in your rounding. So I'm going to scroll back up. All right, so we're going to use a z of 2.58. Z sub alpha over 2. So now it's just a matter of finding our error. So it'll be 2.58 times sigma, which we said was 1.5, times root 20. I'm not a big fan of the TI-83 84s, and I understand that some of you probably don't like Desmos because you got to get your calculator, you got to get your computer out and all that kind of stuff. Desmos is on the App Store if you download and you have it on your phone and all that kind of stuff. So that is E. So I'm just going to call, and what I like about Desmos is I can define things like that. So I'm going to take my 22.9 and I'll subtract E from it. I'll take 22.9 and I'll add E to it. And that then becomes my interval, 22.0346 and 23.765. Okay? And what that means to us is if we were to take an infinite number of samples, okay, of size 20, 99% of those infinite samples are going to capture our real population mean. Does that make sense? Okay, we can be now 99% confident that this is one of those samples that catches our mean or captures our mean. Okay, so our real population mean will be in there, and we'd be 99% confident in that. I think maybe seeing a simulation might help with that. So let's see here. Huh? See what? Awesome. Guys are so messed up. All right. Yeah. We are recording. So it says select a distribution, so I'm going to go normal. Okay. So this is all of our data. Now we don't have. I wish a simulation would show you like the actual data values. It doesn't have. They're in the background, but you can't see them. Okay. But what it's going to do, I think we've seen this before, where it drops down little bubbles like those right there. Okay. And it's going to, so when it drops them down as individual orange values, okay, it is then merging them together. So when it merges them together and gives me that green bubble, that green bubble is a sample mean. Does that make sense? Okay. Now, because my distribution that this is coming from, because my distribution that my samples are coming from was normal, then these are going to be normal. Okay, so I don't have to worry about n being bigger than 30 or anything like that. But let's go ahead and make n go up to 30. Okay, so what it's doing is it's taking 30 raw data values out of my population, and it's finding their sample mean. Each one of those green dots is a sample mean. Okay, and that sample mean is meant to estimate the dotted line that's going through the center of the distribution, which is mu, correct? Does any one of those green bubbles fall directly on that dotted line, like smack dab in the middle? It might touch the dotted line, but is it directly on the dotted line? No, they're going to deviate from that a little bit. Huh?
You missed it. There was one.
The one looks like, yeah, okay. So that one looks like it was, okay. But now understand what's going on here is that the idea is that that little bubble is a point estimate, okay? The point estimate is never a great estimator of the population mean. Does that make sense? Okay? It's very rare. You see it a little bit, okay? And I would still argue that even though the simulation is showing it, that if we were to zoom in far enough, you would see that they would differentiate. They would be different or deviate from one another. So, point estimate, not very good. So what do? We say, okay, we won't be 90% confident. That's what I'm saying right here, okay? And that's what's generating these segments that are going through those bubbles, right? And those segments are equally distant on both sides of the bubble because they are the beginning and end of my interval. And we're seeing then that as long as it is resulting in green as it passes below that second black line, then that means that the segment or my interval has captured the mean. It's passing through that dot, so that segment is passing through that dotted line, right? If it's red, that means that that sample did not capture the mean, and that's one of those 10% times that my interval did not have the mean inside it. Does that make sense to everybody? Okay. So what happens when I want to be more confident? I want to be 99% confident. What happened? I can't zoom in on this side. But those lines become longer, right? And if I'm now 99% confident, those lines become longer. That is probably the only red dot that you'll see as we play this for a long time. Because 99% confident means that my interval is going to capture the mean 99 out of 100 times, essentially. Does that make sense? Okay. If I want to be less confident, see I can't get down to 0%, but these are all red because they're point estimates essentially. That makes sense? And none of them are going to be exactly the population mean. But as I go, maybe I want to be 50-50, and this is calculating, which ones capture the mean, which ones didn't. If I'm 50-50, then 50% of the time my sample is going to capture the mean. 50% of the time my sample is not going to capture the mean. Okay. Well, I mean that's over long term. So we've done the idea of flipping a coin 10 times. I might get 10 heads in a row. So as we let this play, and I let this play for hours, they will equate to 50-50. Does this concept make sense though? Okay. All right. Does anybody have questions on anything so far? That was fun?